Welcome back to the course Energy Resources, Economics and Sustainability. In the past few classes, we have been discussing the environmental impact of different energy production pathways. In the last class, through the simple example, we tried to estimate the quantum of emissions in terms of CO2, sulfur oxides and nitrous oxides that went out into the atmosphere from a rather typical coal-fired power plant. We estimated the amount of emissions were quite huge. So, we understand that a typical power plant that could be powered by fossil fuels leads to a lot of environmental emissions, and they could have degrading effects on the environment in the long term. But have there been some success stories with respect to some of the emissions in the past, which we can learn from and apply the same principles to the current problem of CO2 emissions? So, let us try to look at some of the problems that were seen as major problems in the past, resulting mainly from energy production pathways, and because of concerted efforts by the scientific communities, signing up of international agreements, proactive role by the different governments, these problems could be solved to a good extent. So, we will spend today's class as well as the future classes on understanding some of these case studies. So, the first case that we are going to undertake would be that of acid rain. Now, acid rain entails or acid precipitation as it is known, like it is the return of emissions that are vented to the atmosphere in terms of light acids or even concentrated acids. A typical example could be the different sulfur oxides that went out in the atmosphere. So, we have seen in the last example in the last class that a typical power plant would vent out significant amount of sulfur and nitrous oxides into the atmosphere. So, these sulfur oxides might combine with the water that is available in the atmosphere and form weak acids like hyposulfuric acid, or even the CO2 that is vented out in the atmosphere can react with water to form a weak acid like H2CO3. Further, another possible pathway could be this SO2 sulfur dioxide reacting with the ozone and forming SO3 molecules, and these SO3 molecules can further combine with water to form sulfuric acid, which is a strong acid. Similar phenomena has also been observed in the case of NOx emissions, where the nitrous oxides go and react with the water molecules and form light acids or the weak acids like nitrous acids, as well as stronger acids in the form of nitric acid. Now, the major problem with these kinds of particles of precipitation is that the acids that are formed initially are in the form of aerosols, which means they are very small particles, typically of a diameter of few micrometers, and they combine with the precipitation that is happening in the form of snow or rain and then enter the water bodies. Also, being light in nature, they can easily be transported to hundreds of kilometers. So, it means that the emission source could be very far away from the source where the precipitation is occurring, which is having a acidic character. Further, a lot of you would understand the acidity of a particular medium is measured by the pH value. A pH value of 7 basically indicates water and is neutral in nature, and typically the water bodies around the world are expected to have a pH ranging from 6.8 to 7.4, and this is the normal range in which the marine life also survives and flourishes. What happens when we have an acid rain is the water that comes in contact with the different water bodies or the soil would have a significantly lower pH. Just for an example, vinegar, which is used for the cooking applications, would have a likely pH of around 2.4. Sulfuric acid would have a pH of around 1. If you are talking about different types of bases, they would have a pH of greater than that of 7. So, these like precipitation, which is also called acid precipitation with low pH enter into the water bodies, brings down the pH of these water bodies, and this becomes like not a very conducive environment for the fish or the marine life to thrive, sometimes leading to endangerment and extinction of species. Also, a major concern is that this acid rain, when this falls on the like historical monuments, it leads to the spoil. An example you can see on the figure on the right. Further, there had been an increasing concern about acid rain spoiling the Taj Mahal in India as well. So, this is having a great consequence, as well as the historical monuments are also concerned. Further, if you look in the history, what have been the major instances of extreme acid precipitation in the past, we can come across that there was a storm in Scotland in the year 1974, which had a pH of as low as 2.4, and it made a degrading effect on the local water bodies. Then in the state of Pennsylvania in the US in the year 1978, there was again a rain which was having a pH of 2.32, which is lower than the pH of the common vinegar that you use for cooking purposes. Then in Norway and Sweden, it was recorded that the rains were having consistently a pH that was less than 4.6. Something similar was also experienced in the country of Holland, where like the pH of 80% of the drizzles was less than 3.5 and sometimes as low as 2.5. And a majority of this was basically because of the power production or the energy production pathways, which were primarily like sourced from coal, because a lot of SOx and NOx emissions were going into the atmosphere. And it was also happening that many a times the countries which were suffering from this particular phenomena of acid rain had very little contribution. The actual emissions were happening in a different country which could lie hundreds of kilometers away. So, if we try to look at what were the consequences of some of these extreme events, we can come across that it had a major degrading effect on the marine life of these countries. So, as I have iterated, like the normal operating range for lakes and rivers in terms of pH, the pH should have a value between 6.8 to 7.4, but because of the continuous intake of highly acidic influx in terms of acid rains or acid snow, the pH of many of the water bodies in these observed countries fell below the 6.8 level. As a result of this, there was a shift in the types of species that existed. It gave way to acid tolerant species, which includes the algae and similar species, and slowly you would have noticed like a lot of lakes turned green. And this is also a phenomena that we experience in our countries in a lot of places, because a lot of acid tolerant species, or the acid which the species which are not very tolerant to acid would not want to stay here. And it was also observed that the salmon fish in many of these countries didn't reproduce for a number of years, which brought it near endangered or extinction. Further, it was also noticed that the acid sensitive species like snails or amphipods disappear, and these kinds of species also form a major part of the food chain. The larger fishes or the larger marine life would feed on them. Because of the disappearance of their food, it also affects the entire food chain, leads to the death of fishes. So, it was quite common to see like fishes being dying en masse in the lakes. Another major consequence was that a higher pH also causes a higher concentration of aluminum ions and other metallic ions, and these ions would damage the gills of the fish, which they use for their respiration. And once the gills get damaged, it also helps like the future propagation of the marine life, and also the higher ups, like the animals or the different marine animals which will feed upon this fish, again causing a degrading effect on the complete food chain. And the fishes in return would either become emancipated or they die in the long run. So, these effects were felt in a major way in all these countries in the Europe and the Americas, and there was a big public outrage, and the governments wanted to take a specific target to bring down the sulfur additions. And also, as I have iterated, that in many of the cases it so happened that the source of emissions was a different country than the country which was reaping the effects of these kinds of acid rains. So, as can be seen in this map, the areas marked in green are the areas which led to the which were the source of acid precipitation, which were the major sources of sulfur and nitrous oxides. So, you can see the Americas here and the lower parts of the Europe, and the areas that were suffering from this acid precipitation were different countries. Like you can see the countries like Norway, Sweden and the Nordic countries, as well as Canada was a major sufferer for the emissions that were originating from the US. And this also led to an accelerated effect because there was there was international politics that was involved. The sufferers were not really the originator of the problem, and this helped in accelerating the events where the countries came together, took up the global targets to reduce the sulfur emissions by so and so amount, and to some extent or to a great extent they were very successful. If we see India, the problem is not very much, although we have emissions because of the flow or the air pattern, and also the studies have not been widely carried out, but this problem was widely faced in the undeveloped world as the Europe and the Americas. So, what was the solution to this? So, the solution came into being. It started in the early 1970s and continued till the 80s and the 90s. So, it took around 20 to 30 years. In the US, they set up a target of reducing the SO2 emissions from the one prevalent at 1970s in the terms of 28 million ton per year to around 9 million ton per year by 2010, almost threefold reduction in the total amount of SO2 emissions. Further, the environmental protection agencies of the US also brought in the Clean Air Act, and also developed the market based mechanisms which could help the cap and trade system, which means the industries or the different kinds of corporations which were the major reasons behind the sulfur emissions had to cap their emissions by the targets set by the government, which were becoming stringent year by year. Further, there might be some companies or corporates which were overdoing the target. So, these companies had the opportunity to sell their further emissions to the corporates or the industries which were unable to meet the target, so as to incentivize the good performance, whereas to penalize the poor performance. It also helped bring down the total cumulative emissions. The industry which was having or outdoing its performance in terms of emissions had the ability to make monetary benefits in terms of selling the emissions to a particular industry which was not able to do so because of certain constraints. So, for the companies could realize the capital investment that they made for capturing of the SO2 into the air quite fast. And because of these policies, we can see the SO2 emissions could drastically reduce in the Americas as well as the Europe. So, this is the data how the SO2 emissions have been increasing. So, we see with the influx of the industrial revolution, there has been a great increase in these emissions, particularly in the Americas and the Europe, and it peaked around somewhere around 1970s or 1980s, and beyond which, because of the efforts by the different government agencies as well as the public perception, there was a drastic reduction in the amount of SO2 emissions in terms of million tons, and we can see how the reduction took place in the year 2010 in the different Americas as well as the Europe. Whereas a part of concern would be that in India or China or a majority of Asia, the SOx emissions still tend to rise. And this means that we should be following some similar policies that the Americas and Europe have followed almost 30 years back, and bring down the levels of SO2. So, this is something that we should learn. There have been policies which have worked from them, and they have been successfully been able to achieve the set targets, and many of those targets were achieved well beyond the deadline. So, the solution, one of the major solutions that was employed in particularly the coal-fired power plant was the use of calcium sulfate for the capture of the SO2. This is also called the flue gas desulfurization. So, normally you would have the coal and the air entering the boiler which would be combusting the coal and providing in the heat for raising the steam, and this steam is then used in the steam turbines for the production of electricity. The flue gas from these boilers would normally go to a cyclone separator for the removal of ash, and further particulate matters get removed in the electrostatic precipitator. What is left in the flue gas is a majority of nitrogen, carbon dioxide and the sulfur dioxides, and that sulfur dioxide is made to react with water. So, what is sprayed on this flue gas is the limestone solution, which is limestone dissolved in water. So, first the water reacts with the sulfur gas to produce hydrogen sulfide, and this hydrogen sulfide is then made to react with calcium hydroxide, which is nothing but lime, to produce calcium sulfate as well as water, 2 molecules of water, and this is a precipitate. This is in the form of solid and quite easy to separate. So, this is one of the methodology that was adopted in the developed world for capturing the excess amount or the capturing a majority of sulfur dioxide that was coming from the coal based production of electricity. Further, we have also seen a lot of industries as well as the power plants also shifted from coal to natural gas. That again in turn helped in bringing down those emissions, because a majority of these emissions came from either coal based power plants or the use of crude in the refineries. So, let us try to understand the application of this kind of process with the help of an example. Let us consider the power plant that we have considered in the previous class. So, the power plant had a nominal capacity of around 400 megawatt of production, and the thermal efficiency that was taken was around 37%. It was burning on anthracite, which is a high grade coal, and the calorific value is quite good in terms of 29,000 kilojoules per kg. We approximated that the coal would have around 1.2% of sulfur, and this sulfur is by weight. The anthracite is all again expected to have almost 94% of carbon, and it is desired that we use the limestone solution for in the flue gas desulfurization unit, and it is also expected that this particular solution or this particular methodology is able to extract almost 99.5% of the sulfur dioxide from the flue gas. Now, let us try to determine the amount of calcium hydroxide and the calcium sulfide that would be formed on a per day or a per year level if we were to use like the same process. The underlying equations would be SO2 reacting with H2O providing in H2SO3, and further this H2SO3 reacting with calcium hydroxide to produce 2 molecules of water and 1 molecule of calcium sulfide, and this is a solid in nature and could be easily separated. So, let us move to whiteboard to gain a better understanding. So, this was the calculation that we undertook. So, just for the sake of revision, we had the power plant producing almost 400 megawatt of electricity. The efficiency was 37%, which is here. The power input that would be required would be almost 1081 megawatt or 1081,000 kilowatt. This was the power input, and if we would have to look at the energy input, I would multiply this with 60 seconds into 60 minutes into 24 hours. So, this gives me the energy input on a per day basis, and this heat would primarily be supplied by coal, for which I know the calorific value to be around 29,000 kilojoules per kg. I divide the total energy input by the calorific value of the coal to give me the consumption of coal in terms of kgs of coal per day. Further, we also estimated the SO2 emissions in terms of 0.012 into 3.22 into 10 to the power 6. 0.012 basically refers to the 1.2% of sulfur being the component of coal, and 3.22 into 10 to the power 6 is the amount of coal that was being used on a daily basis. So, further my emissions were around 38.64 into 10 to the power 3 kgs of sulfur. This was the emission of sulfur, and further this reacted with oxygen to give in sulfur dioxide, and the sulfur emissions that came were finally 77.3 into 10 to the power 3 or 77.3 tons of sulfur dioxide on a daily basis. So, let us start our calculation from this very point, wherein the SO produced is available to us And now I would want 99.5% of sulfur dioxide is captured. This is the assumption that I am undertaking. So, SO2 removed specific would be 0.995, sorry, into the amount of sulfur dioxide that was used, that was around 77.3 into 10 to the power 3 kgs per day, and this value would come around to be 76.9 into 10 to the power 3 kgs per day. So, this is the amount of sulfur dioxide that I would expect to be removed on a daily basis. The underlying equation would be the sulfur dioxide reacting with water, and this gives me H2SO3, and this H2SO3 then reacts with calcium hydroxide CH2 to give us 2 molecules of water plus 1 molecule of calcium sulfate SO3. So, I would have almost 64 grams of SO2. This reacts with water and would produce H2SO3, and this H2SO3, 1 molecule again would react with calcium hydroxide, which the molecular weight would be 74 grams, and would produce 2 molecules of water as well as 1 molecule of CaSO3 with a molecular weight of 120 grams. So, all in all, 64 grams of SO2 to be captured would require almost 74 grams of calcium hydroxide and would produce 120 grams of final product. So, if I would have to estimate the amount of calcium hydroxide that is consumed, this would be equal to 76.9 into 10 to the power 3 into 74 divided by 64. This value would roughly come out to be 88.9 into 10 to the power 3 kgs per day. So, this is the amount of SO2 that would be, calcium hydroxide that would be consumed on a daily level. So, it would be around 88 tons per day, which is again a huge amount. Further, if we want to have a look at the production of CaSO3, we can write a similar equation wherein we have 76.9 into 10 to the power 3 into 120 divided by 64. So, this is the amount of CaSO3 that would be produced. If I solve it, this would come around to be 144.2 into 10 to the power 3 kgs a day. If I look at the yearly values for the production, so the value of calcium hydroxide. If I look at the yearly production of calcium hydroxide, this would come around to be around 32,449 into 10 to the power 3 kgs or 32,000 tons on an yearly basis. And if I go towards the production of CaSO3, and this would be roughly 52,628 into 10 to the power 3 kgs per year. So, often it was noticed that the production level of this precipitate, like in terms of the CaSO3, could be quite huge on a yearly level, and this required a specific landfills because the production was around 50,000 tons per year. So you would need a dedicated landfill for the disposal of products like this. So it also turned out like sometimes the solution to one of the problems also led to other problems in terms of disposal. And it also need a good amount of feedstocks in the form of calcium hydroxide, which was needed to the tune of around 32,000 tons a year. So let us go back to the slides. We have tried to estimate like how this problem was solved in the energy industry, where coal was used for as a source of energy. Another major source of the sulfur emissions was also the refineries. So refineries were also consuming crude, and this crude was having some amount of sulfur which was vented out to the atmosphere. And so the industries took in different pathways for that, and one of the pathways that was adopted was the close process or the oxidation reduction process. It's a redox process, and the major aim was to capture the sulfur. So the sulfur was first made to react, or the sulfur bearing compounds in terms of this R refers to the hydrocarbon chain, and we have the sulfur attached to it, was made to react with hydrogen by bubbling the hydrogen through a column, and the result was the H2S gas as well as the hydrocarbon. Once the H2S gas or the hydrogen sulfide gas was formed, it was made to react with oxygen to form one molecule of water and then sulfur in the form of solid. And this sulfur was later on used for the production of sulfuric acid, which could fetch the company's market value. So the major the major pathways that was adopted in the form of closed process was the reaction of the hydrocarbon chains with hydrogen to produce H2S and the hydrocarbon, and because hydrogen was involved, this was the reduction process. And this H2S gas was later on made to react with oxygen, forming water as well as sulfur, and sulfur that was produced had another market value, and this is the oxidation taking place, and that is why it is also called the redox process. The other pathways that was adopted also included the use of fluidized bed reactors, which could make the reactions in the fluidized bed itself. The sulfur that was produced, as I have said, was in the solid phase, and it was normally used in the production of industrial sulfuric acid. And the low sulfur liquid products of petroleum in the form of gasoline and diesel were often found to have a market value higher than the high sulfur products, and this was another incentive for the fuel companies to go for this low sulfur production, low sulfur fuels, because it could help get a good market share as well. Some other ways which was used for the removal of sulfur was the use of fluidized bed reactors in the coal-based power plants. So in a fluidized bed reactors, we have the whole bed acting like a fluid because of the huge influx, and in that fluidized bed, the calcium hydroxide was mixed so as to capture the sulfur in the bed itself. Then and there was also a switch from using of low sulfur coals from high sulfur coals. Then companies have also been switching to using natural gas as an energy source, or a mixture of coal and natural gas. Then the old coal-fired power plants, which were not very efficient again, as well as had a good amount of emissions of sulfur, were either retired or they were retrofitted with new SO2 scrubbers. There was an increased demand side management as well, and also the companies were encouraged to purchase power for power generation which were using low sulfur coal or other fuels which were not causing as much emissions. So if we see the trends in the different countries, let me show you the trend how the sulfur content or the sulfur dioxide have been decreasing in the country of UK. We can see there was a significant decrease. So the reduction could be almost 90% as compared to 1970 levels. So there has been a huge reduction in the sulfur dioxide levels. and these levels were also a lot of time coupled with other emissions in terms of the NOx emissions, because these the source of these kinds of emissions remains similar. So we also saw that similar methodologies and similar kind of pathways also led to a similar decrease in the NOx emissions, and the NOx were again a major source of acid rains as well, and the efforts that were taken in for the removal of sulfur also acted, or a complementary effect was that there was a decay in the nitrous oxide emissions as well. So to sum up, or this particular examples is that like the SO2 emission reduction happened quite fast in the major countries of the world, and further the industry at the onset were not very keen on adopting the methodology, because it came in the form of the different capex investments. So it was estimated in the US that the companies might have to incur somewhere between $1 to $2 billion of investment, which the companies were not willing to make. And as we have understood in the previous classes as well, the era before 1980s was that like in which companies would see like the environmental regulations in a negative tone, and they would not want to spend much for the betterment of the environment. But further, because of the government policies, and the targets were set and the companies were made to adopt the emission targets. Further, it was realized that the companies ended up spending only 25% of the original estimates. So the all the savings or the drastic reduction in the SO2 emissions came at 1/4 of the cost that was initially estimated. And a large part of the abatement cost also helped in increasing the efficiency of the process, because new equipments were put in the power plants which were much more efficient and were good for the overall economics of the power plant, which helped the power plant owners make profit. Further, it was also expected that there would be some major disruptions in the power sector that might occur because of the change of the earlier equipment with the new one, but nothing of those sort was felt, and the inconvenience that was put to the consumers were also almost negligible. So this brings us to the example that we have seen in the last class, that the change in the business perspective with the coming up of new and innovative ideas, like major environmental problems could be averted, the emission targets could be met, and of course there were the capital expenditures, but they could be vastly reduced, and a lot of expenditure also helped in increasing the profits in the future. So this is one of the case studies with respect to SO2 emissions, which is seen as an environmental case study, or the case study of environmental emissions, which is a success story, and that could be adopted in countries like India and China, because we still are growing the sulfur emissions as the country is concerned, and we can adopt these kinds of methodology for a further reduction. And similar kind of methodology is also seen as a worthwhile case study for the future implementation of CO2 abatement. With that, we end today's lecture. Thank you.